Hello, my name is Rakesh Ravi, and I'll be presenting the Physics 2212 Lab 1 charge tapes. Okay. The purpose of this lab is to study charged pieces of tape and estimate the excess charge on each one. To create charge tapes, we press strips of clear tape onto a base strip struck to the table, then peel them off quickly. This process transferred charge, leaving the peeled tapes charged. We then suspended one charged tape vertically and observed that it floated above another charged tape when they were about 3 centimeters apart. From these measurements and a computational model, we determined that each tape carried about 1.4 times 10 to the negative 8 coulombs of charge, or roughly 8.7 times 10 to the 10 electrons. This lab uses three main physics ideas: Coulomb's law for the electric force, Newton's law for gravity, and equilibrium to set them equal to each other. When the tape floats, the upward electric force equals the downward gravitational force. To simplify, we assumed both tapes carry the same charge, the charges were concentrated at the tape center, and we ignored air resistance. These approximations let us model the floating condition mathematically. Alright, we prepared U-tapes by pressing one tape onto a base tape and peeling it off quickly. This charged tape was suspended vertically. We measured the tape length as 20 centimeters, the width as 1.9 centimeters, and calculated a mass of about 2 times 10 to the minus 4 kilograms. The floating distance was about 3 centimeters. In the free body diagram, the suspended tape experiences gravity pulling down and an electric force pushing up, which balances at the floating point. On to calculations. The gravitational force on one tape is the mass times gravity, which is about 1.96 times 10 to the negative 3 newtons. At float, the electric force must equal this value. Solving with Coulomb's law gives a charge of about 1.4 times 10 to the negative 8 coulombs per tape. That equals roughly 8.7 times 10 to the 10 electrons. Compared to the estimated atoms on the sticky surface, only about 2 times 10 to the minus 7 of them exchange electrons, showing that even a tiny fraction of charges can produce significant forces. All right, onto our GlowScript computation model. To check our results, we modeled the system in GlowScript. We represented the tape as two spheres separated by 0.03 meters and reused our electric field function from Lab 0. By setting one tape to 1 coulomb, we calculated the field per coulomb at the other tape. Balancing the electric and gravitational forces again gave us about 1.4 times 10 to the negative 8 coulombs. This visualization showed the upward electric force and downward gravitational force with equal arrow lengths. To make the math manageable, we used three main assumptions. First, we assumed both tapes had the same amount of charge. This is reasonable since they were prepared in the same way. Second, we treated each tape as if all of its charges were concentrated at the center, even though in reality, the charges spread along the tape. This simplification allowed us to apply Coulomb's law directly. Third, we ignored air resistance, since the floating condition depends mostly on the balance between electric and gravitational forces. As for errors, one important source is charge loss from the handling. Touching the tape allows charges to leak away into your skin, reducing the measured force. Another is uneven charge distribution, because peeling the tape might not apply charge in a uniform manner. Finally, there are small measurement errors, such as reading the 3 centimeter floating distance or estimating the tape's mass from its length and density. These could all shift the numerical values slightly, but the overall conclusion remains. So, if electrons are positive and protons were negative, our observations would not change, because like charges would still repel and opposite charges would still attract. Only our label of positive and negative would flip. It is also important to handle the tapes as little as possible, because when the positively charged tapes touches a neutral hand, electrons flow from the hand into the tape, neutralizing its charge. This reduces the electric force and prevents the tape from floating. In conclusion, our experiment and model agree that each tape carries about 14 times 10 to the negative 9 coulombs of charge, which comes from only a tiny fraction of surface atoms losing or gaining electrons.